Okay, but I didn't do it also before. When was it?
When you picked up the bottle.
Okay. I see, okay. All right, good. So the first problem was H infinity control, and the lesson we have to take is whenever I have a certain LMI, which I can cast as a QMI in terms of the unknowns, in this case A and B, I can easily cook up the data-driven version of the same problem. Okay? The second problem I'm going to look at is dissipativity analysis from data. Well, first of all, I want to talk about dissipative systems. I'm going to define mathematically what dissipativity means, and I'm going to discuss the physical intuition behind it. So we start from an input state output system. X is state, U is input, Y is output. They have corresponding dimensions. X is n-dimensional, U is m-dimensional, Y is p-dimensional. Is this too close, maybe? Is this better? And also, I have this symmetric matrix, m plus p times m plus p. M and p are number of inputs and number of outputs. Okay? I'm going to call star system dissipative with respect to the supply rate, this supply rate, given by the symmetric matrix S, if there exists a semi-definite P such that this dissipation inequality holds for all times and for all trajectories u, x, y of the system star. So this is a bit of a mouthful definition. And it seems to be also a mathematical definition. There is no obvious reason why I look at this property. But there is actually a very good reason. This supply rate is a quadratic one. It contains terms like u times y. And if I have an electrical circuit, V, voltage, times I, current, has a physical meaning. And typically, power, energy correspond to quadratic variables, quadratic quantities in terms of variables. And there is also the dissipation inequality here. What does this mean? Well, this is basically abstraction of what we know from physics. No system generates free energy. And what this dissipation inequality tells is the following. P or X transpose Px represents the energy stored in the system at time t. And this inequality says that the energy stored in system in future cannot exceed the energy stored in the system in the past plus the energy we put in the system. But it is a mathematically abstracted version of this very sensible energy conservation principle. there is a positive feedback here. So I'm trying to solve it as a control engineer. Huh? There should be an optimum point. Maybe we should run a data-driven algorithm to figure it out. Is it better if it is higher? Is it? Okay. And so basically it says, along all trajectories, I have energy conservation. Huh? But in an abstract way. And it is normal because I don't know what this X represents. X may represent certain physical quantity like voltage or current in an electrical circuit, but it may be also charge and flux. I don't know what X is really representing. But I can abstract this energy conservation principle in this way. I have this supply rate. It represents the energy we extract or put in the system, depending on the sign. And this dissipation inequality says that the energy dissipates, actually. I cannot generate more energy than the stored energy plus the supplied energy, it says. And indeed, there is a historical background to dissipation, dissipative systems. It all started from circuit theory. Every circuit containing resistors, inductors, capacitors, transformers, gyrators, and so on is passive in this sense, dissipative in this sense with respect to a certain supply rate. And in 1972, Jan Willems wrote a paper called Dissipative Dynamical Systems. It has two parts. So it is like how many years ago? 53 years ago. And came up with this abstract definition of dissipativity, which covers many interesting cases. And well, if this dissipation inequality is satisfied, then this function, x maps to x transpose px, is called the storage function because it resembles the energy stored in the system. And two very important examples of dissipative systems are given by this choice of supply rates. The first choice says that S uy is equal to u transpose y, like in circuits. If u and y are voltages and currents, for instance, then this is it is the power u times I. M is equal to P, and this is called a positive real case. It is also called passivity. And the other case is this choice of S, which is related to H infinity performance, actually, because it says that the system has a H infinity performance less than or equal to gamma, if this is the case. But this is a more mathematical way of studying dissipativity in a general way, rather than focusing on passivity or L2 gain. So it has many, many applications in systems and control, not only in systems and control, also in circuit theory. We have seen already one. The L2 gain or H infinity performance corresponds to this choice of supply rate. Okay? So this is a story for the model-based case. I am given this system, I am given this supply rate, and I ask myself whether the system is dissipative with respect to that supply rate. And it is so if there exists a P satisfying the dissipation inequality. Well, I can write down, obviously, this is not easily verifiable because I need to parameterize somehow all, or I need to test it for all trajectories. But I know a parameterization of all trajectories, so I can use that. Indeed, if I now look at the dissipation inequality, this is the energy stored at time t. This is the energy stored at time t plus 1, and I have this supply in between. But what I know is that x of t plus 1 is given by in terms of x and u at time t. And here also y is given in terms of x and u. That I can plug it in. If I do that, this is the first term. Everything is in terms of xu now. X transpose p x. And if you look at here, zero identity xu is going to give me u. Cx plus du is going to give me y. So this is the second term. If you look at here, identity xu is going to give x. A b xu is going to give me x of t plus 1. Therefore, this is the right-hand side. But the nice thing about this, this way of writing it is that now everything is in terms of xu vector. So if I take xu transpose from left and xu from right out, then I'm going to look at this inequality. Agree? And this is supposed to, this has to be satisfied for all xu trajectories. Right? But therefore I can drop these because they are completely free. The system does not restrict values of xu, instantaneous values of xu. Which means that star system is dissipative with respect to the supply rate given by S if and only if there exists a semi-definite P such that this linear matrix inequality is satisfied. If I know the model, if I know A, B, C, D, the only unknown here, I know the supply rate, the only unknown here is P. And this last one is a linear matrix inequality. Agree? Now, as before, I have to start to set up the model class. Unlike the previous cases, this time I have also outputs. I have inputs, states, and outputs all at the same time. So I look at this model class now, where W and Z are both noise terms, and I assume that AS, BS, CS, DS are unknown, as well as W and Z are unknown. In the H infinity control, I assumed C and D to be known. This time, I assume C and D to be unknown. Okay? And I assume that I can collect input, state, output data. So these data are given. Now I collect noise terms entering in the state equation and noise terms entering in the output equation into a big matrix V, and assume that V satisfies a certain quadratic matrix inequality, as before. Then the set of data consistent systems is going to be all A, B, C, D, satisfying this this linear equation for some V minus satisfying the blue quadratic matrix inequality. Huh? So it's not that much complicated, but it is a little bit different because this time we also have CD are unknown. As before, of course, I can solve V minus from this expression, substitute here. That is going to eliminate V minus, and I'm going to end up with a QMI in terms of A, B, C, and D. Huh? So this gives me this set of data consistent systems now. All A, B, C, D quadruples that satisfy this green quadratic matrix inequality. And then you see this time, not only I have input and state, but also the output measurements. And these are just algebraic manipulations, just a little bit different than what we have done so far, but essentially the main principle is the same. So I have this data consistent systems, and at the end of the problem, I want to analyze the dissipativity, so I define the data to be informative for dissipativity with respect to a given supply rate. If there exists a semi-definite P, if there exists a semi-definite P, if there exists a semi-definite P, such that star, I don't feel like it is working, but it does work. If there exists a semi-definite P, such that this star inequality is satisfied for all A, B, C, D in sigma. Okay? Now, the nice thing now is that I can easily write this as a QMI in terms of A, B, C, D. So I don't need to have some matrix acrobacy like H infinity control problem. It is immediate. So if I take this as partitioned, then this thing is equivalent to this LMI, QMI. Yes. Yes. Yes, yes. But this is just for presentation purposes. If X is not available, you can still solve the problem, but it is going to be too technical to explain in a presentation. I'm going to explain stabilization on the basis of input-output data next, and then you will see what I mean by technicality. No? But it is not a major obstacle. The idea is important here. Once you have this idea, you can work out different scenarios, like without a state, just input, output, and so on. But let's see why star is equivalent to this blue quadratic matrix inequality. Well, I think it is enough to write star just a little bit different, and then the rest is going to be immediate. I am going to write star in the following way. I take P0, 0, P minus P, and SUY, this is S matrix partitioned. And zeros here. And I write I0AB here and 0ICD here. because this is block diagonal, I'm going to have AB related part times P related part times AB related part plus CD related part times S related part times CD related part. So it's going to be exactly equal to star. Huh? And to obtain what I have here, I need to simply swap the first and third row and column blocks of this matrix. So, sorry, second and third row and column blocks of this matrix. And that gives me exactly this one. So this is nice, or nicer, I should say, comparing to H infinity, because we obtained the QMI immediately without going through this long sequence of manipulations, first Schur complement and then multiply something, define a new variable, take the Schur complement again and so on. We have already a QMI in ABCD. So this is good news. But I am over 50, and if I know something about this life, if there is good news, there is an immediate bad news. And it is the following. This is the QMI for the green one that gives me the set of data consistent systems. And the blue one is for the dissipativity analysis. But I cannot apply matrix S lemma because there is a kind of blood mismatch. I have A, B, C, D here, and it's transpose here. So this was the strict matrix S lemma. As you see, I have Z here as unknown, Z here as unknown. But now I have A, B, C, D in one, and it's transpose in the other one. So I cannot apply matrix S lemma. Unless, of course, there is a way to pass from Z to Z transpose while keeping the quadratic matrix inequality. If there is a possibility to write a quadratic matrix inequality in this form in terms of Z transpose as another quadratic matrix inequality, then I would change one of them and then apply matrix S lemma. Right? So the first point is there is this mismatch of the unknowns here. And the second point is we have seen only strict matrix S lemma, right? Henk, can you tell me if we haven't seen the non-strict version? No? So this is not strict as you see. I cannot directly apply strict matrix S lemma. So I need to do two things to begin with. Somehow change from ABCD to its transpose. And secondly, I need a certain matrix S lemma for non-strict inequality. If I can manage these two, then I can write down conditions on data for dissipativity analysis. And then what should I do? Well, we have the cookbook. I have many cookbooks at home. I have a couple of Indian cookbooks at home. I like Indian food very much, but I can't cook very often because it takes too much time. I'm not a good cook, so I have to follow the recipe. And then all these spices, I have to check, was it 1 tablespoon or 1 teaspoon? I'm not a very quick cook, but I cook by looking at a cookbook all the time. So I'm used to the fact that one needs to use a cookbook. And here's a cookbook. And the obstacles I mentioned can be overcome by using results from the cookbook. And the nice thing is, even if you don't have this paper, all the results that are necessary are in the lecture notes, in the mathematical preliminaries chapter. I forgot which chapter it is, third chapter, I think. So now, here is what we call dualization. Before going through the mathematical details, let's look at this part only. You see, it says one quadratic matrix inequality in unknowns Z is equivalent to another one in unknowns Z transpose. And that is exactly what we need. Now let's read what is required for that. It says P is a symmetric matrix, it's fine. And if P is, it assumes P to be non-singular, then this quadratic matrix inequality in terms of Z is equivalent to this in terms of Z transpose, where this pi sharp is obtained by inverse of pi, multiplying it from left right by these identity zero related matrices. Now, if I look at the blue quadratic matrix inequality I obtained from dissipativity analysis, then I can write it in this way if both P and S are non-singular. If P and S are non-singular, this big blue matrix is going to be non-singular, and therefore I can apply that result and write this one, where R matrix is obtained from this multiplication. As long as P and S are non-singular, then I can convert this one, which has A, B, C, D as an unknown, to this one, the purple one, where A, B, C, D transpose is an unknown. And once I do that, I need another ingredient, non-strict S lemma. And it also is available to us. It's about Mn, but this time, instead of strict inequality for M part, I have non-strict. And the result is the same if and only if there exists a non-negative alpha such that M minus alpha n is non-strict, as we can expect. But there are certain conditions on n, which are, they are important, of course, but for the purposes we have now, they are kind of secondary. Now, let's look at the bigger picture again. I have this quadratic matrix inequality, which gives me data consistent systems. Let's say this green matrix is N. And there it contains, as usual, the noise model and the data. So I have the noise model, the data, I can compute N. And dissipativity QMI, I converted to a new one, which is given by this matrix M. And now, as you see, the unknowns are the same type, transpose of A, B, C, D matrix. Therefore, I can apply the non-strict matrix S lemma from the cookbook. But there is a catch, of course. This is valid only if P is positive definite, P is non-singular, and S is non-singular. So I have to make some assumptions to guarantee that. And here are the assumptions. If the supply rate has exactly P negative and M positive eigenvalues, then it's going to be non-singular. And then one can also show then storage function needs to be positive definite. This is for guaranteeing P and S to be non-singular. And this is to guarantee that we can apply matrix S lemma. And under these two conditions, we can prove that the data are informative for dissipativity with respect to the given supply rate, if and only if there is a positive definite Q and a positive number alpha, such that this inequality is satisfied. So, in the first problem, H infinity control, when we wrote the matrix inequalities for the system to satisfy, we could not recognize easily that one can write it as a QMI in terms of unknowns. In that case, it was AB pair. After some manipulations, we were able to do that, and then we use matrix S lemma strict version. In the second problem, it was very easy to come up with a QMI in terms of the unknowns, ABCD matrix, but there was a mismatch between the QMI defining the data consistent systems and dissipativity. To overcome, we use this dualization result, which changes the variable to its transpose while keeping the QMI structure. Okay? And there is yet another problem, stabilization from input-output data, in which, as we will see soon, we need another technique to help us to finally obtain QMI implies QMI, and we can apply matrix S lemma. Okay? Sure. P. Mm-hmm. Mm-hmm. Yeah, P inverse. Very good question. I can explain. I didn't explain all the details, but here is the theorem. Okay. To begin with, if this LMI is feasible, then we are done. And we have a positive definite storage function. I can take the inverse of Q, right? But the other way around, I do not know that the storage function needs to be positive definite, right? It's just greater or equal to 0. But thanks to this particular assumption that S has exactly P negative and M positive eigenvalues, first one can prove that if the data are informative for dissipativity, then the storage function needs to be positive definite, which I totally skipped. Once it is proven, then you can also prove that this is it's just a Q is P inverse. Yeah, it is indeed so, but if you look at the structure here, let's look at this part. If alpha is 0, because of minus Q, it's never going to be satisfied. So it is indeed, the S lemma says it has to be greater than or equal to 0, but because of the structure here, it has to be positive. Yeah, minus Q. It's never going to be satisfied because of minus Q. Q needs to be positive definite, so. Any other questions? And so stabilization from input-output data. Now, okay. There were many reasons for me to like India very much, because I had many Indian friends, and we also have a long history. I am from Turkey, between India and Turkey. But yet another reason was I like very much behavioral approach, and India was one of the very few places on this planet where people showed interest and studied behavioral approach. So the point of behavioral approach is the following. Of course, I will keep it very short. Maybe I can explain from my experience why behavioral theory is important. I am supposed to teach mathematics students systems and control theory. Okay? And these students are not engineering students, so they don't have any engineering kind of intuition or so. They come to the classroom, they know mathematics, no engineering, and I'm supposed to teach them. Okay? So what shall I do? Well, I go to the classroom and I start writing things like okay, I say, let's look at the system x dot is equal to ax plus bu. Y is equal to cx, where u is input, x is state, y is output. Oppa, I lost all of them. They have all these questions. What do you mean by input? What is state? Where does this come from? Why do we call it a system? And then you are doomed. It's a difficult thing. Also, it is difficult because they are younger and they question everything, which is very good, of course. For me, it is granted. This is a system. Everybody knows it's a dynamical system, linear time invariant. But for them, it is not so. Of course, the main point of behavioral theory is not to teach math students systems and control, but let's think about it. What do we mean by a system? Is this a system? Or is it a representation of a system? Now, what is the mathematical object, essential mathematical object we are looking at? It is the difference between linear operator and its matrix representation. Like the derivative on polynomials, for instance, is a linear operator. If I restrict the degree of polynomials, I can write down a matrix representation for it if I choose a certain basis. But that matrix representation is not the essential object to study. The derivative operator is the essential object to study. And I don't need to work with these matrix representations. Very often, it leads to difficulties, actually. And from conceptual point of view, it is also not a good idea to focus on matrix representations because it depends on the choice of the basis. So the entire point of behavioral theory is to define a dynamical system. A dynamical system is basically a collection of certain trajectories. And this is a very, very universal thing. It's not about systems and control. Think about Kepler's laws. It says for the motion of planets, certain trajectories are allowed, certain trajectories are not allowed. If you think of solar system as a dynamical system, then certain trajectories are allowed, certain trajectories are not allowed. So there is a collection of allowed trajectories, possible trajectories, and that is the behavior of the system. Huh? Also from modeling point of view, if someone gives me an electrical circuit, you all have studied circuit theory, right? Someone gives you an electrical circuit, there are resistors, capacitors, inductors. You are supposed to write down the equations. Huh? What do we know about electrical circuits? Well, we can zoom in. If you have a resistor, I know Ohm's law. For inductor, capacitor, I know the constitutional laws. And then I have Kirchhoff's laws for voltages, for currents. But imagine I am a computer. I am very stupid, therefore. What can I do? I can follow a recipe, right? I can write down for every junction Kirchhoff's current law. For every loop, Kirchhoff's voltage law. And then the elements corresponding laws. I can write all of them together. Then I need to somehow come up with this model. You see, this is not natural, because from the circuit I didn't land up there. It is even worse if I want to write a model for some pre-specified variables. Like I have a circuit and 2 ports, and I want to write the model of the circuit by using only the port variables, but not the internal ones. I can write down this model, but I have to get rid of these auxiliary variables which I use in the intermediate steps. These are all not natural. The most natural setup is to start from higher order differential or difference equations rather than the first order one, because that is what you are going to end up with after modeling any physical system. So this is a very quick explanation of behavioral theory. So we need to look at, and especially if you are dealing with input-output or external variables, then behavioral theory is a must. I was a PhD student in the Netherlands. Jan Willems was very much pushing for behavioral theory, and it was not picked up because it was like, I can do everything in the state space anyway. You do HA infinity control, well, I did it already. You do dissipativity analysis, well, that was done already. So you don't do anything new. That was a typical argument against behaviors. But all of a sudden, since 2020, in the last 5 years, there is a surge in interest in behavioral theory because of data-driven control problems. Of course, to make it practical, you need to work with input-output data, and there you immediately lose state space representation because you don't have a representation. You have only data. And you need to use behavioral theory. But I know some big shots in our field who even made fun of behavioral theory and people doing behavioral theory 20 years ago. Now they are dying to write papers about behavioral theory. It's just funny how these things work. But behavioral theory helps one formulating problems and solving problems without using representations of systems, or the problem tells which representation is better than another one. So I hope I'm going to convince you with the particular problem I'm going to study next. Stabilization from input-output data. Okay? Technical details are not important. The core idea is important. So, to begin with, I have input-output data. So, if I start from a state space representation, as we are going to see tomorrow, writing down the set of data consistent systems is impossible. And also the geometry of data consistent systems is a very complicated one. Maybe I should already highlight this point because only then one can appreciate what I'm going to do next. Let me explain what I mean a little bit more precisely. Suppose I have this system and I can access only inputs and outputs. Okay? Let's assume that I know the dimension of X, n. And I want to find out all systems that can generate a given set of data. And so somebody gives me some data. Input-output data. I know n, and I want to figure out all A, B, C, D, such that this is satisfied. I'm going to take U minus and Y minus as we defined before. U minus is this matrix. And Y minus is this matrix. And then I need to find A, B, C, D, and X minus X plus, such that these equations are satisfied. If I fix n, right? But there is also a hidden constraint between X minus and X plus. They are not completely arbitrary. The first column here in X plus is the second column here in X minus. There is a shift property. But this is not a linear equation. You cannot solve it. Given U minus Y minus, you cannot easily find even one quadruple of A, B, C, D, and some X satisfying this. It's not possible. It's not going to be, even if you think about this set, it's not going to be convex. It's not going to be even connected, I don't know. You have only very, very limited knowledge about the set of all A, B, C, D that can generate the given data. And this was the case where I know the state space dimension. Now imagine I don't know the state space dimension. So there is no way that one can really continue from now on as we have done before. I cannot write down this A, B, C, D. I cannot write it. It's not going to be a QMI if I have, for instance, noise and so on. I am doomed. So I have to start from another representation, which allows me to work with inputs and outputs directly without going through state, which I do not have access to. And by the way, state is a completely unnatural concept. It is not, it doesn't have any meaning from physical point of view. It's a mathematical construct. If you have an electrical circuit and ask the electrical circuit, what are your states? It's not going to say voltages and currents. It can be voltages and currents. It can be fluxes and charges. It can be any linear combination of these. State is not a physical concept. It's just something we like to use as a tool. Okay? But do we agree on this point? If we want to work with inputs and outputs only, we have to give up state space thinking anyway, because it doesn't go anywhere. I mean, I can write down this set, all A, B, C, D, such that there is an X satisfying this, but then I can't do anything with it. It's very difficult to understand what kind of a set I am looking at even. Huh? All right. It is also because I can make state space transformations, right? Since I don't have X. If A, B, C, D is one of them, any state space transformation gives me yet another one. So it is going to, it's not going to work. That's why there's a surge in the interest to behavioral systems, because if you want to deal with data-driven problems starting from input-output, and that is the most interesting case anyway, you have to study these problems in the behavioral context. So I'm going to look at autoregressive models instead of state space models. Now, let's discuss what autoregressive models look like. I have a to-be-controlled system. It is given by this difference equation. Y is the output, U is the input. There are definitions in behavioral theory for input variables and output variables, but I cannot, of course, start from scratch. And these P and Q are matrices of appropriate sizes. Again, I have P outputs, M inputs. Okay? And I start with a particular one because, as you see, this is the highest delay term here, and the corresponding coefficient I take identity to for presentation purposes to make it a little bit less unreadable. Okay? This L is the order of the system, I call it. It is the memory. It's related to the memory of the system. And instead of carrying out these P and Q matrices with me all the time, and writing this expression all the time again and again, I'm going to use this shorthand notation. P of sigma y is equal to Q of sigma u, and sigma is the shift operator, and P and Q are polynomials. So if you look at P, for instance, C to the power L means that you have to shift L times, which is going to produce YT plus L. And then this says you have to shift L minus 1 times. It's going to produce this thing, and the coefficient is the matrix P L minus 1. Okay? There is an intimate relationship between such autoregressive models and the state space models. I'm not going to go into the details, but every such autoregressive model can be also written into a state space model and other way around with some extra even properties. Is this clear? We have these P and Q polynomials, and this expression I can write in a very compact way by using polynomial matrices. So a system then is this equation. I can represent a system by such a compact representation. In particular inputs, then I'm looking at such a system. P of sigma y is equal to 0. I call it autonomous because there is no input, and the y trajectory, since there are no inputs, depends only, the future of y depends only the past of y. Any questions? Now, since we are interested in stability, I need to define and study stability in this behavioral context. I'm going to say an autonomous system given by this P polynomial is stable if all trajectories tend to 0 asymptotically. It's the same kind of definition we have in state space. Now, one can show that an autonomous system is stable if and only if all roots of the determinant of P of Xi, P of Xi is a polynomial matrix, it's a square one. I take the determinant, it's going to depend on Xi. And all the roots of this polynomial must be in the open unit disk. It's not very unexpected, right? In particular now, if I have this state space system, this is an autonomous system, right? For this, I can choose P Xi as Xi identity minus A. Xi for this shift, A times constant, right? What is the determinant of this thing? Well, determinant of P Xi is equal to determinant of Xi minus A. Therefore, this tells me that all eigenvalues of A, because the roots of determinant of Xi minus A are the eigenvalues of A, all eigenvalues of A must have magnitude less than 1, as we know. State space case is a particular case. But since I want to work with data, I want to have something I can check without computing determinant and so on. What did we do in state space case? Well, to study stability stabilization, we looked at Lyapunov inequalities. For stabilization, for instance, we looked at this particular Lyapunov inequalities of this sort in stabilization, for instance, right? Huh? And this was in closed loop, but in general, if I have an autonomous system, then A is stable, I know, if and only if there exists a P such that, positive definite P, such that this Lyapunov inequality is satisfied. Right? And the nice thing is that even though this P is a polynomial, so I have a higher order system, I can still come up with a Lyapunov characterization of stability. Huh? So this is the P matrix. So such an autonomous system is stable if and only if there exists a psi greater than or equal to 0 with this dimension, P times capital L, which satisfies this matrix inequality, where bold P is this matrix, which collects P matrices. Huh? Since the highest coefficient is identity, it is automatically non-singular. Because of this identity here. But if I have PL here, then I need to assume it is non-singular. And so I have a Lyapunov characterization for stability of higher order systems. What do? Well, I take these coefficients, put in a matrix, bold P, and then I look for a semi-definite psi which satisfies this inequality. I'm not going to prove it, but this can be proved. This is proved already in behavioral theory, in particular by using the so-called quadratic differential forms. Now, there is an entire analog of state space theory in terms of behaviors. Stability, all these properties can be checked by looking at the higher order representation without writing the higher order representation into a first order representation like state space. And in particular, if I have such a P, then this is the LMI generalization of something like P minus A transpose P A from the state space theory. Okay? So I have 2 more hours, right? Or, okay, Tushar says 3 even. So as you see, I'm getting close to the end. But now, if we start from a higher order autoregressive model, I know how to assess stability of an autonomous system. That's what I know so far. Well, there is a little observation here, some sort of, but basically the idea is to write star in a different way, and it follows from the following observation. Now, imagine that I write this IPL by zooming in. This is the first P by P block, and the remaining is here. I can always do that. And if I now look at this LMI, because of this I, psi, this I, I'm going to have psi. And if I now use this green part, if I define this green part as J, the remaining I can write also easily in terms of psi. I want to get rid of this this structure here, which I didn't like. Okay? So I replace this structure by this structure with the cost that this J is a constant matrix. It's just They are just equal to each other, this big expression and then this seemingly more compact expression. But if I do that, one of the reasons I do that is to work with something more compact. Another is the following. This psi was supposed to be greater than or equal to 0, right? But if I look at this now, I see that psi needs to be positive definite. Psi needs to be positive definite because psi is greater than this term, which is semi-definite. So psi needs to be positive definite even. Huh? Okay? But I know how to assess stability of autonomous higher order systems. Huh? Therefore, from this theorem, I can pass to this theorem. It is essentially the same, but I can replace this non-strict one to a strict one, and also write the star inequality in a more compact way, where J is a fixed matrix, P, bold P, contains the coefficient matrices P0 up to Pn minus 1. So I'm done with stability. And now I want to design controllers. Sorry? Yes. Yes. For non-autonomous systems, there is no notion of stability. Only if I take input to be 0, I can talk about stability. Sure. Yes, that you can do. But since I'm interested in stabilizing a system, I'm interested in autonomous case and ordinary stability. Of course, if you are interested in different sorts of stability, you can do that. So now I start with the system to be controlled system. L is the order of the system. I define these polynomial matrices, and therefore I can write the system in a compact way. And for autonomous systems, I know how to assess stability. And now I choose a controller. What does a controller mean in this case? It is yet another system that I'm going to attach to the to-be-controlled system. So if I make a diagram, I am given an input-output system, which is given by the pair PQ. So maybe I should write it down. P of sigma y is equal to Q of sigma u. I think I have the diagram on the slides, by the way. I think I forgot about it. So I don't need to draw on the board. So this is the to-be-controlled system. U is input, Y is output. I want to come up with another dynamical system, which is going to take this output Y as input and produce an output which I'm going to feed to the original system as an input. And the to-be-controlled system is given by P and Q polynomial matrices. I'm going to take controller given by G and F polynomial matrices. And I'm going to assume, again, the coefficient of the highest power term here is identity and 0 here. Okay? What is the closed loop system? Closed loop system is going to be given by this autonomous system. Because this is going to be an autonomous system. There are no inputs anymore. And it is going to be given by this polynomial matrix. And the question now is, given given P and Q, that's the system, find G and F such that this autonomous system is stable. Huh? And I do know how to assess stability of an autonomous system. Agree? Now, in closed loop, I have this autonomous system. So if I look at this polynomial matrix, I can identify these coefficients. Huh? Let's write these coefficients down. Now, I do know how I can check stability of of an autonomous system of this form. Now, if I replace this P by this bigger matrix, I obtain the Lyapunov characterization of stability of this closed loop system. Huh? For that, I need, let's see, I need the coefficients here, which means that I need these coefficients, right? Huh? But in these coefficients, what I know is QP matrices. What I don't know is GF matrices. So I separate what I know and what I don't know. In C, C for controller, I collect the coefficient matrices from that come from controller. And in R, I collect coefficient matrices that come from the system. So C is like the first row block here, and R is like the second row block, or related to the second row block here. Then I can now replace P by these coefficients. And if I do that, P is going to be C on top of R. Then the Lyapunov characterization tells me that if I am interested in stabilizing one system, this R is given, I want to find a psi and C such that this inequality is satisfied. And psi is positive definite. And this is the design problem for a given single system. R is given. I want to find a psi and C, psi positive definite, satisfying this matrix inequality. And it is not a linear matrix inequality. Why? Because C and psi are unknowns, and I have terms like C transpose times unknowns times C again. I have quadratic terms involving unknowns.
The distance of this G and F pair is
G and F, yeah. What kind of thing?
Case. So you just say as a critical solution.
This one?
Yeah. Then we can say that C, we can essentially will get the F where I was just asking where any way by which we can guarantee that always this has a solution I minus.
This one.
Yeah.
Yeah, of course, that's a good question, because in state space theory, we know the answer. AB needs to be stabilizable, right? And it is the same here. Let me think. Yeah, basically this original system given by R needs to be stabilizable. But I'm not going to assume it. The LMI is going to tell me. And this is nice because I have this matrix inequality, and then this is the design problem given R. I am looking for psi and C, psi positive definite, that satisfy this inequality, which is not a linear matrix inequality, but I can, again, manipulate it a little bit. But let's now switch to the data scenario. This was all for a given higher order system by this P and Q, by this R, P and Q. If I go back and use the diagram here, purple system is given, and I'm looking for the green system. And then for this scenario, I have an answer. Maybe not complete, but I have an answer nevertheless. What I want to do is now write down the data setup. So, as the model class, you see at the very beginning of the, well, not at the very beginning, in the second day, we introduced data informativity framework, and the first ingredient was the model class. Later on, we focused on mainly state space models with input states or inputs, outputs, and so on. Now, we have an example in which we don't have state space models, but we have a different kind of model class. And this is the model class I'm looking at. Yes?
The previous slide, without data case, no data case. How do you normally solve this equation?
Again, you make a Schur complement trick to get rid of this. Yes, but it is the same as in state space, for instance. If I look at this characterization, it is not an LMI because I have P, B, K. But if I take the Schur complement, then I'm going to have unknown times unknown, since the P the inverse of P is a positive definite. I can define the product as a new unknown to make it linear. So one needs to do similar tricks here as well. Okay, here is the setup. I'm looking at this model class. P and Q are polynomial matrices. W is noise. I take a particular form for P and Q, namely the coefficient of the highest term here is identity and here is 0. These are also technical assumptions which we can avoid. And then basically I am looking at this left-hand side, and that needs to be equal to W, the noise, process noise. And among, within this model class, I have a pair PS, QS unknown that represents the true system. I collect input-output data. No state, because there's no state anyway. And then I can write the following. If I collect inputs and outputs in one vector, let's say V, then VT plus 1 up to VT plus L I can write. If I multiply this vector by this matrix, then I'm going to get the left-hand side here. Because minus Q0 is going to multiply U of t. P0 is going to multiply Y of t. Minus Q1 is going to multiply UT plus 1, and so on. And this is just a way of writing the left-hand side here in a more compact way. But from here, I can do the following. This part, apart from zero identity, I defined as R. Okay? Now, if I look at this expression, then it is R zero identity times This is for T0. This is for T1. This is for the last term, T minus 1. The first column is going to give me W0, the second W1, and finally WT minus L minus 1. I'm trying to figure out the data consistent systems. What I know is that this needs to be satisfied by the noise and the system parameters. And what I know is this data, finitely many data. So I write data into this green Hankel matrix. And when I multiply from left by R0 identity, it generates me the noise matrix. It's an immediate consequence of the starting point. And again, I need, so let's write this in a compact way. So I can write this as R times some part of this matrix, the upper part except the last row block, and 0 identity times the rest. So I can define then this green matrix I can take as H1, H2. I can partition it. Is this clear? Look, what I'm going to do is, there is this 0. What does this 0 do? 0 identity multiplies the last block here. What is this last block? V of L is U of L, Y of L. This 0 is going to get rid of U of L. So I'm going to have Y of L. So if I define this part as H1, then it is going to be R times H1 plus Y vectors, which I write as H2. That needs to be equal to W minus. Now we are in business. Because this green guy comes from data. This R is a data consistent system. And the only thing I need to make is an assumption on the noise. Here's the assumption, the usual suspect. W minus is unknown, but satisfies a quadratic matrix inequality. And now, if I substitute this term here, it is going to give me a quadratic matrix inequality for R, which represents a data consistent system. Now I am in business. If somebody enters this room with a noise model and data, I can find this green matrix N, and then any R that satisfies the green quadratic matrix inequality represents a data consistent system. And in particular, the true one belongs to this set sigma, because I collected the data from the true system. So from now on, instead of writing this big matrix, I'm going to write N, a green N. And you may ask, like, why do I do that? Because these matrices become bigger and bigger, and yesterday night, at a certain point, they didn't fit on the slides. So that's why I started to give them some names to make them shorter. We don't need to remember what N is. What we need to remember is I can find out N from the data and the noise model. So this is the set of data consistent systems. Now, remember the notation, C for controller, and all these coefficient matrices are unknown, and R is for the system, and these coefficient matrices are coming from the data consistent systems. Okay? Now, this is Lyapunov characterization of design problem for a single system. So what I need to do is to define the corresponding informativity notion. I'm going to say that the input-output data are informative for quadratic stabilization if there exists, it should be, if there exists C and psi such that psi is positive definite and this thing is also positive definite for all R in sigma. And J is this constant matrix. And this is the analog of what we defined in state space case, but written for AR case, autoregressive case, and nothing more. Again, we require systems to be stable with a common quadratic Lyapunov function. Okay? All right, now it's time for the question you asked a couple of minutes ago. This thing contains products of unknown terms and therefore is not easy to work with. Instead, I'm going to use the Schur complement. So if you look at this left-hand side, it is the Schur complement of this matrix with respect to psi inverse. Okay? Now, if I look at this big matrix and take its Schur complement with respect to psi, then I obtain this matrix inequality, where I have psi inverse as an unknown, and C still as an unknown. Now, if I define psi inverse as omega, I can write this matrix inequality in the following way. This term is related to data consistent. I am trying to write it in terms of, I am trying to write this term, this inequality, as a QMI. In terms of R this time, because R is the unknown. And I can do that indeed. So it gives me a QMI, where this M matrix contains omega, C, and J. J is known. I have also a color convention. Whenever I have these matrix inequalities, red variables are unknowns. And green ones are fixed, given. And so first I obtained, let's go back. First I obtained a quadratic matrix inequality for data consistent systems. Now I obtained another quadratic matrix inequality, this time for feedback stabilization. Okay? So I am almost there. But if I write these by defining this as M matrix, if I write this, again I have an obstacle. I can't use matrix S lemma. Why? Because this guy has unknown R transpose, but this guy has R transpose times a matrix as unknown. Huh? As you can imagine, there is a way to tackle with this. Otherwise, I wouldn't explain all this and say, sorry, we cannot solve this problem. We go back to the cookbook, and from the cookbook, we find this theorem. Let's see what this theorem says. It says, start with a Q plus R by Q plus R symmetric matrix. Partition it into 2 by 2 blocks, where one block is of dimension Q by Q. and assume that pi 2, 2 is positive, and its Schur complement, the Schur complement of pi with respect to pi 2, 2 is positive semi-definite. Then it says for y and w given these dimensions, there exists a z satisfying pi quadratic matrix inequality and also this linear equation, z times w is equal to y, if and only if y satisfies this quadratic matrix inequality, where the matrix, defining matrix, comes from pi and w in this way. Basically, it says if you have a quadratic matrix inequality where pi satisfies these conditions, together with some linear equation, it is nothing but a quadratic matrix inequality, but in terms of this variable y. This looks like a very complicated statement, right? But it doesn't say anything more than the following. Remember, what is the geometry of these quadratic matrix inequality sets? They are ellipsoids. I'm going to try to draw a 3D ellipsoid now. It's not easy, but I will give it a try. Oops. I will give it a try. Sorry? It is not visible. Oh, no. Okay. Okay. Is this better? But let's make it three-dimensional, huh? It's a three-dimensional ellipsoid. Huh? So this z QMI, let's say, z variables satisfying that QMI are points on this three-dimensional ellipsoid. There is one more equation, linear equation for z. What are the points of z satisfying that? It's a affine space, right? It's a plane. It's something like a plane here. So you have an ellipsoid, you cut it with a plane. What does the intersection look like? It's going to look like an ellipse. You have an ellipsoid, you cut by a plane, the intersection is going to look like an ellipse. And this is what it says. If you're an ellipsoid, the first quadratic matrix inequality in terms of pi, and the plane, they are intersected because that satisfies both of them. It says it is nothing but yet another ellipsoid, but in smaller dimensions. And what is the relationship between this projection and what I'm aiming at? You see, here I have the product of R transpose and this constant matrix. It is like Z times W. So I can convert this M QMI to a QMI where only R appears. Or, sorry, the other way around. I can convert this one to an LMI where this appears. But is this point clear? I can convert one QMI together with some equality constraint to another QMI. And that's what I want to do. If I do that, Huh? If I assume n22 is less than 0, so I can write this QMI now with this variable. And I need to multiply by W transpose W from left and right, and this is my W. If I do it on N, I obtain N hat. Okay? Now, if I go back, I have two QMIs with the same variable. Huh? Therefore, I can use matrix S lemma. Okay? And I did use matrix S lemma. The data are informative for quadratic stabilization if and only if there exists a C and omega, where omega is positive definite, such that this matrix inequality is satisfied. Where does this N hat come from? It comes from the noise model, the data, and multiplication by this matrix and this matrix. Okay? Well, is this an LMI? No. That's bad news. Can we cast it as an LMI? I'm not going to do it. We are all tired, I know. But the answer is yes. Like we did before, by using a Schur complement argument, we can cast this matrix inequality as a linear matrix inequality. Okay? And then from that linear matrix inequality, we can find out, if it is feasible, we can find out this C, which is going to be a controller. Now, 41 out of 43, which means I have 2 more slides. We are all tired, we are all hungry, but we must have also have the feeling that we achieved something. And we did indeed. We looked at 3 problems. H infinity control, in which we ended up with an LMI which was not so obvious that it can be cast as a QMI. And by using Schur complement kind of ideas, we were able to do it. And the lesson is, basically, whatever design or analysis problem you can imagine, which is characterized by a linear matrix inequality for model-based case, we can write down a data-based case. It just needs to be massaged if necessary. That was the message of the first example. The message of the second and the third example is common, but requires different techniques. The message was, sometimes you have 2 quadratic matrix inequalities, but you cannot directly apply matrix S lemma because they do not have the same type of unknowns. But there are at least 2 techniques. One is dualization, which takes a certain unknown and comes up with a QMI with unknown, the transpose of the unknown of the original one. And the second one is projection. Sometimes you have a QMI where the unknown appears as after multiplied by a matrix. There, I can use the projection result to write it down as another QMI. And once the 2 QMIs have the same unknown, we need to pick a matrix S lemma, depending on whether we have strict or non-strict inequalities. And the application of that matrix S lemma yields the final result. And this is a proper cookbook, right? I mean, I explained you a general recipe now to solve all sorts of problems in the data-driven control setting, right? And all these lead to conditions on data. Given data are informative for something, design analysis problem, if and only if data satisfy some conditions. All the results we have seen are of this nature, right? It is very nice, of course, and it is very, I always tell my students that they can impress their family members or friends by saying, give me a matrix, I'm going to find the singular value decomposition of the matrix and so on. We can impress people. Somebody enters this room and says, look, I have this data, can I design an H infinity controller? We put the data on a computer and say yes or no. But still, it is a kind of incomplete story if we compare to model-based control. Because in the model-based control, typically, if I want to design a controller, there are certain requirements that has to be satisfied by the system. And if those requirements are satisfied, there is always a controller which does the job. But now, within database systems and control theory we explained, within this data informativity framework, that part is missing. Because if the data are informative, I am able to design controllers. But if the data are not informative, I do not know what to do. Imagine I have a stabilizable system, but I don't have informative data to stabilize it. So it's incomplete because I do not know how to generate informative data. These are all the problems we studied, exact data, noisy data. The red ones are those we studied during the lectures, and the blue one is was in the tutorial session. But in all these problems, we have statements like data are informative if and only if some conditions are satisfied. If these conditions are satisfied, then we can design controllers. But if they are not satisfied, the theory doesn't say anything more. To complete these results to an equally perfect theory of model reduction, one needs to say how we can obtain informative data given per problem. Right? Well, we don't know it yet. We have some preliminary results. We know how to do it in principle. We have a certain idea. It seems it's working, but it is something much harder than producing these conditions, informativity conditions. But if we want to attack this problem, how can we devise experiments? By experiment, I mean I want to apply an input to the system, read out the output state, whatever data I can get from it. By looking at the data I have, and also the problem I want to solve, I want to apply the next input. It produces an output. Now I have more data. I want to look at this data and also keep in mind what problem I want to solve and apply another input. Okay? If we want to attack this one, of course, we have to fix a problem first. I want to obtain informative data, but for what? Stabilization, H infinity control. For what? Now imagine we want to attack this problem. Where should we start? I think easiest option is to start from system identification. So we go back to where we start. In the first lecture, Henk explained to you, if you have a persistently exciting input, you can collect the output and find out the underlying system, well, up to a state space transformation. Now, it is very easy to cook up examples for which you can have input which is not persistently exciting, but still leads to identification. So if we are going to embark on a general research agenda of developing online experiments per problem, maybe first we should understand how we can design an online experiment for system identification. Because it is very nice, persistently exciting inputs and subspace identification, because I don't care what kind of system I have. I just apply an input. I don't do anything in between. It's offline. I collect all the output and then identify the system. But if I have a particular system at hand, when I start applying inputs, u of 0, it returns y of 0. And subspace identification does not use the information I can extract from y of 0 at that point. Instead, blindly applies another input sample. And it yields another output, but it doesn't use that output. It uses the information obtained from the output only at the very end. It's an offline scheme. Applies the input, collects the output, and then does some computation. But if I am interested in identifying a given system, wouldn't it be more natural to apply one input, see the reaction of the system, and decide what output I'm going to apply next? Because I want to identify the system as soon as possible. Right? And that is what we are going to do tomorrow as the last day. We are going to study online experiment for system identification. So the outcome is going to be an online experiment. Apply a certain input, look at the output, and by looking at the input and output, apply another one. Collect the output, another one. That is what we are going to do. But first, it's going to be a duo. So first I'm going to talk about informativity for system identification, because so far we only know a sufficient condition for system identification, persistence of excitation, but it is not necessary. First we are going to study necessary and sufficient conditions for data informativity for system identification. Once we obtain those conditions, then we will ask ourselves how we can design an online experiment to identify the system as soon as possible. Okay? Any questions? Let's have lunch then.